Okay.
Um, so good morning, everyone. Thank you very much for joining our MCTP colloquium for today. So it's a pleasure to have Professor Zvi Bern from UCLA. So Professor Bern is an expert on scattering amplitudes. So he's been working on this computational scattering amplitudes. I think I remember very this one loop revolutions that's
Right.
I think it's initiated by these black hat collaborations that Professor Byrne and I think Lance Dixon and Dave Kosover started. So and now Professor Byrne is working on scattering amplitudes in relation to gravitational physics. So Professor Byrne has received numerous awards. So I think one of them that I will highlight is in 2014, he received the Sakurai Prize with Lance Dixon and David Kosover. This is for his work in constructing one-loop amplitudes using the string-inspired method. And he recently received the Galileo Galilei Medal from INFN in Italy, also together with Lance Dixon and David Kosover. So yeah, Professor Bern, it's a great pleasure to have you here in our colloquium. And today he will be talking to us about quantum scattering amplitudes and gravitational wave. So yeah, please, the time is yours.
Okay. Thanks a lot, and I am really sorry that I can't go in person, and also that I couldn't go to the Amplitudes conference that was in Korea. I definitely would like to visit Korea and visit the East in general. So today I'll be talking about applications of quantum scattering to the problem of precision gravitational waves. Um, Okay, so first, the basic outline of what I'll be talking about is first explain a little bit about quantum scattering amplitudes, what that is, how that works. I'll show you the connection to gravity, gauge theory and gravity. If effective field theory is something that we use as a basic idea in everything we do. The concept of unitarity, which I'm sure you're familiar with from quantum mechanics. That's something fundamental that we use in all our calculations. There is something specific I want to show you relating gravity and gauge theory. That's these double copy relations, which are precise mapping from gauge theory amplitudes into gravity amplitudes. And it's something that we use in all our gravity calculations. It's a very slick way of doing things. And the heart of the talk is the applications of these ideas to state-of-the-art precision gravitational wave computations. And then we'll talk a little bit about the outlook. So where did scattering amplitude start? And of course, probably the very first place would be Rutherford's scattering experiment. Alpha particles come in, they hit the gold nuclei, and then they scatter. And we can describe this classically or quantum mechanically. And from this, you can deduce the basic interactions. That's how we know there's a nucleus. So we know that it's the electric potential that governs this and so forth. And today, it's the same basic ideas as back then, except we get much more sophisticated using quantum field theory, is Feynman diagrams, and so forth. But this is a subject that has a long history going back to Rutherford. And today, the topic of scattering amplitudes, the modern theory of scattering amplitudes, reaches in many directions. Its origins were in collider phenomenology. Actually, at the time, it wasn't the LHC, but it was the Tevatron. And that feeds straight into QCD, understanding QCD amplitudes. And then it was very fruitful to look at the supersymmetric cousins of QCD, the super Yang-Mills theories. And as soon as we understood the Super-Yang-Mills theories, we then understood those same ideas can be transported to gravity theory, supergravity theories. There's a connection to string theory. The very basic ideas also flow out of string theory and back and forth, amplitudes and string theory. There's connections to more mathematical subjects and also new formulations of fundamental physics. That would be the amplituhedron. There's lots of connections to mathematics, the mathematics of polylogarithms. Multi-iterated integrals is something that's a big deal, and where we use mathematics to understand the types of integrals that we get. And there's other connections which are more theoretical, Grassmannian's algebraic geometry, which the Grassmannian's, it connects to the amplituhedron. And today I'll be talking about the connections to gravitational waves and more generally classical gravity, how to use these ideas for understanding those problems. So just to make sure we know what we're talking about, the scattering amplitudes we're talking about are the ones that are used as quantum mechanical descriptions of events at particle colliders. So you can have a proton comes in, proton goes in, and then stuff comes out. So this would be actually a Higgs event at the CMS collider. Proton comes in this way, another proton comes in that way, and there's a collision here. And you get a spray of particles coming from the quarks and gluons that are inside the protons. And I'll be talking about tree level. When I say tree level, just think of lowest order of perturbation theory. I'll also be talking about loop level. I'll talk about loop diagrams, loops. Those are higher orders of perturbation theory. And of course, the pioneer that we follow in much of this, it's of course Richard Feynman. And these scattering amplitudes, they're a foundation for understanding particle collisions at colliders. Much more goes into it with the initial state and the final state and how to interpret it, but you could say the core interaction right here is described by these diagrams, and more generally the scattering amplitudes, which these diagrams describe. Now, what's this scattering amplitudes field? What's it about? Well, the way to explain that is with one example. Like maybe the best example is, in a sense, what started the field, and that would be looking at the lowest order of a 5-point amplitude. That's these tree diagrams. And suppose you had a homework assignment, go evaluate this. You can open up your standard textbooks, a little bit older textbooks, let's say Peskin and Schroeder, and you would follow the Feynman rules, and you get something like this. If you look here, you'd like zoom in and see what this is. It's dot products of momenta and polarizations. And this is actually a small piece of the answer. This is about a 25th of it. So you'd look at this and you say, well, okay, these Feynman rules, they can give us the answer, but obviously there's no structure here. And you could stare at this for as long as you like. You won't really find very much in these formulas. Now, the reason why you won't find very much is, of course, you're looking at it the wrong way. You should look at it the right way. And it took a while to understand this. And the idea, this is in the early 80s, people started understanding this, is you should be looking at the scattering amplitudes using the helicity. You shouldn't be using polarization vectors. The polarization vector, it has too many degrees of freedom. There's 4 degrees of freedom. We should actually be talking about 2 degrees of freedom, the 2 polarizations of a gluon, or it could be a photon. And the natural way to do that would be using circular polarization. This would be the circular polarization vector. Now, of course, you want to do it in a much slicker way than this very clumsy way written right here, which would only be valid along the z-axis. And that's where spinor helicity comes in. It's sometimes called Chinese magic, Zhu Zhang and Chang, they wrote down this formulation, which we use today, the spinor helicity formulation, and it's basically describing these polarization vectors in terms of spinors, spinor inner products. These are spinors as a reference momentum, which should drop out of any physical gauge invariant answer. And you can take a homework assignment and take these polarization vectors and verify that it satisfies everything that circular polarization is supposed to satisfy. Therefore, they're perfectly valid polarization vectors. Now, there's something cute that happens when you start looking at the polarization tensor of gravity. What you discover, if you're looking at the positive helicity polarization of gravity, you'll discover that it's in fact can be written as a product of two polarization vectors of gluons or of photons. And it factorizes in this very simple way. And at first sight, you might say this is not very profound, that this is just a consequence of group theory and you know, nothing terribly interesting here, just kind of an accident. But in fact, this is the tip of an iceberg. So this factorization you see here, it doesn't hold just for the linearized theory of gravitons, free gravitons, traveling without interaction. This actually works for the full theory of Einstein gravity. The entire nonlinear theory also has this factorization. And that's something we're going to exploit. By the way, this follows from the great identity that a spin 2, that you can represent it as a product of spin 1s. You have to subtract out certain of the lower spin states, but basically it's 2 equals 1 plus 1. Spin 2 can be written in terms of 2 spin 1s. By the way, just like you can take the spin 1 and write it in terms of 2 spin 1/2s. Okay, if you do that, then what happens is that 5 gluon amplitude I showed you, that it simplifies enormously. So this page and that page have the same information, except this page is only a piece of it. Here, all the information is contained in a very compact way in terms of helicity states. And right here was the birth of the field of scattering amplitudes, the modern version of scattering amplitudes. It just took about 20 years before people actually knew there was a new field. It took a little while longer, but right here, as you could say, where the field was born. Okay, and these ideas, you can use this to go to higher and higher orders of perturbation theory, the loop diagrams. And that would be through using unitarity. There's a method called generalized unitarity method. And it's basically a set of sewing rules that tell us how to take all the simplifications at the lowest order, this would be a tree amplitude, and put them together, sew them together, so that you get higher orders of perturbation theory. And the sewing, it's done with these intermediate states on shell, meaning they're physical and gauge invariant. So once you have a simplifying relation at tree level, whatever it may be, that automatically gets imported into loop level. So that's how we go to very high orders, and we can study all sorts of things in gravity, supergravity, and also we use this also at higher orders in gauge theory. And these ideas, this led to what's called the NLO revolution in QCD. So that's a while ago. That was mentioned in the introduction. And what we're going to do here is apply the same ideas to gravitational waves, high orders of perturbation theory. So it'll be high loop orders. In fact, these pictures here, the generalized unitarity, they come from our paper on gravity. And I should add that it's not just the normal ideas of unitarity, like a 2-particle cut, a 3-particle cut. You can have these generalized type cuts that allow you to build these loop amplitudes from the simplest pieces possible. And there's an organized way of doing this, which I'm afraid in this colloquium, there isn't enough time to explain exactly how that's done. But suffice it to say, there's a set of rules, and you can use lower loop information to build higher loops. So it's the tree level information that then feeds in to building up the entire perturbation theory of whatever theory you're interested in. Okay, now let's switch to gravity. So normal people, when they do gravity, the place you start is from Einstein's equation. And Einstein's equation, as we all know, what it does is it takes an energy momentum tensor and it turns it into the curvature of space and time, right? And the key idea is geometry, that it's a geometric theory, that we should be thinking about geometry to understand gravity. Okay, that is not how we work. We work in a very different way. We like Einstein's equation. I'm sorry, we like Einstein. We don't use his equation. And we don't use his equation at all. We start from someplace different. We start from Feynman's observation that all of Einstein's gravity follows if we assume the existence of a massless spin 2 particle. Once you assume that, then you are forced into something equivalent to Einstein's equations just by the consistency of the theory as a quantum theory, as an effective field theory, a low energy effective field theory, and you demand that the interactions be consistent. And from there, you can order by order in perturbation theory build up all of Einstein gravity. And that was something understood by Feynman. What we do here is we turn that idea into a practical tool. That's the way we compute. We find this to be very convenient for a set of problems that are in perturbation theory. As soon as you say the word massless spin 2 graviton, it means that you're working in perturbation theory. So in flat space, you're assuming the existence of this excitation. Now, you might object and say, but nobody's ever seen a graviton. No one has ever measured it. Do they really exist? Okay, I'm not going to answer that, but I'll answer something else. I don't know if they exist, but I sure know that they're useful. So it's just an idea that we use, and we can go to very high orders of perturbation theory, reproduce previous results and obtained by Einstein's equation, and then go beyond what was obtained in the past. Now, this is not something suitable for all problems. For some sets of problems, you certainly would like to do it geometrically, not perturbatively. Okay? But at least for a certain class of problems, including the gravitational wave problem, this is a tool we can use. Actually, here's a nice quote from Steven Weinberg, which is basically a guiding philosophy for us. So Steven Weinberg, if you go look in the preface of his book on gravitation, that's, by the way, a beautiful book. You should go look at it. Anyway, in the preface, he says, by now the passage of time has taught us not to expect that the strong, weak, and electromagnetic interactions can be understood in geometric terms, and too great an emphasis on geometry can only obscure the deep connections between gravitation and the rest of physics. Okay, that is indeed exactly the way we think, and we're going to make precisely this philosophy a tool that we use to calculate. We're going to find the connection between gravity and gauge theory, use the information from gauge theory in order to do our calculations in gravity. Okay, so what are the complications with perturbative gravity? Suppose you're an eager graduate student and you say, okay, I'm going to go work on Einstein gravity. Let me go calculate some orders of perturbation theory. It could be classical perturbation theory. It could be quantum perturbation theory. And the way you would start would be from the Einstein action, or you could start the equations of motion, but that's equivalent to looking at the action. And then you do a perturbative expansion, maybe around flat space, or it could be another metric. And then you have some excitations, that would be the graviton field. And very quickly, when you do that, there's an infinite number of interactions. It's a highly nonlinear theory, and the nonlinearities pile up, and it looks pretty complicated if you start inspecting these vertices. Without some very clever choices, it's really terrible. And if you compare that to gauge theory, the interactions, let's see, in a Yang-Mills theory, they stop at the quartic order. There's nothing higher. Now, those of you who've worked in QCD know it's a pretty complicated theory, but compared to gravity, it's a much, much simpler theory. The interactions are much simpler. And your conclusion might be that, oh, gravity is very complicated, much more complicated than gauge theory. It's hard to make progress in perturbation theory. And if you look at the three-point interactions, it would confirm exactly what I told you. This is from DeWitt's paper, the basic paper on gravity perturbation theory and field theory. And we can compare the vertices. There's a 3-gluon vertex. Okay, we all know this from the textbooks. There's a color factor. There's a kinematic factor. It's a little bit complicated, but not terrible. The 3-graviton vertex gets out of hand very quickly, and that's because first there's a sim here that says you're supposed to symmetrize this expression in the graviton indices. A graviton is a symmetric tensor. You're supposed to symmetrize. There's hidden in this notation, see the P6? That means there's 6 terms. It's the permutations, the independent permutations. And if you add this up, it's pretty bad. There's more than 100 terms. And the conclusion is perturbative gravity is a mess. If you're a clever student, you'd probably tell your advisor you should go work on something else. But in fact, that conclusion is completely wrong. You should be looking at it the on-shell way. You should be thinking about these gluons, gravitons. You want them on-shell. In the perturbation theory, you want to devise a perturbative method that everything is on-shell. Okay? All external states to any amplitude should be on-shell, including these 3-point amplitudes, these 3-point functions. If you do that and you use the on-shell conditions, well, that's Einstein's relation, E squared minus K squared is equal to 0. And then you also would like to use the fact that the physical gravitons are transverse and so on. You clean things up and you discover very quickly that the only thing that satisfies the gauge invariance that has the proper properties is in fact 2 copies of Yang-Mills. That's a double copy. There's a connection here. See this connection? The gravity vertex looks like it's built out of 2 of these kinematic factors of the gauge theory. And that's no accident. Okay, and this is the first non-trivial example of what we call the double copy, that the Einstein gravity can be understood as 2 copies of the gauge theory. Okay. Now, in 1985, string theory gave us the clue we needed to unravel what's going on. The first big clue of what's happening here. And that was relations that were derivable inside string theory. Not completely trivial, I might add. There's some work to be done to actually extract this from string theory, but much more apparent than field theory. And it's a statement, literally, that if you look at the lowest order perturbation theory, the tree amplitude, so there's 4 gravitons, 1, 2, 3, 4, that you can literally write it as a product of gauge theory objects, which are also gauge invariant. These are called color-ordered gauge theory amplitudes. They're pieces of gauge theory amplitudes that are gauge invariant, and it gives you a precise relation. That's an equal sign here. Okay, you have to put in the right coupling constant, but up to the coupling constant, that's an equal sign. Okay, and the 5 points, they did it all the way to 6 points, and in fact, you could generalize it to any number of points at tree level. This is all at the lowest order. So what do you learn from this? Well, something extremely profound. Gravity is derivable from gauge theory. And if you look at the Lagrangians, to this day, it's just not obvious. There's no known way that you can start from a Yang-Mills Lagrangian and you could see that this could be true. There's no apparent reason for it. No one has derived it. There's no derivation that explains in any good way how this works, why this works. Okay, you can, of course, verify. The modern tools are powerful enough that you can get to quite high orders or quite high numbers of legs and directly check that these expressions are true, starting from Lagrangians. But why exactly it's true, even to this day, we don't know. We don't have a good explanation. We just know it's true. These things have been proven repeatedly in all sorts of different ways. And the other thing that's actually very surprising is that you might think that there needs to be a string theory behind this, that it's really only whenever there's a string theory that lives above the theory you're interested in. That's actually not true. We apply it, for example, to Einstein gravity as it appears in our universe, not some other universe, not a supersymmetric universe, our universe, where we can use these relations for relating Einstein gravity to gauge theory very directly. Okay, and this was understood back in 1985. It took a while before the importance of this was really appreciated. Another way of looking at the same thing, a repackaging of what Kawhi, Llewellyn, and Tai did, is this duality between color and kinematics. And what's very surprising is if you're interested in the secret of perturbative gravity, the answer is not to be found in perturbative gravity. The answer is to be found in gauge theory. And that's based on a few observations. So let's look at it again. There's your 3-gluon vertex. You have the color factor, there's coupling constant, and there's a kinematic object, a kinematic factor here in the vertex. Now, the color factors, we know a lot about that. We know that the color factors of gauge theory, that they're based on a Lie algebra, and most importantly, they obey a Jacobi identity. Since there's an algebra behind it, that means that we have these consistency identities on whatever these structure constants are. That's the Jacobi identity. Now you can go home and try an exercise. You take a 4-gluon amplitude and you use Feynman diagrams. You can work at any gauge. At 4 points, it doesn't matter. And you pick your favorite gauge, you write down your diagrams, and then what you do is, if you have a 4-point contact diagram, which you would have in Feynman gauge, for example, you look in here and you say, okay, is there a color factor that looks like the color factor of one of these other diagrams? And you just take that term and you put it in there and use this great identity. 1 is equal to S divided by S, where S is this Mandelstam invariant that gives the Feynman propagator, 1 over S. Okay, this didn't have it, so I better put it back in by using this great identity. And I do that for all the terms. I assign that according to whatever the color factor is. I put it into these 3 diagrams. So then I can write the amplitude, a 4-point amplitude, as, okay, there's a coupling constant. There's a kinematic numerator that comes from doing all the algebra on the numerators. And there are these color factors which come from these FABCs. And there's my propagator. And I write it in this form. And we know that the color factor obeys the Jacobi identity. for some definition of the way the legs are ordered. Here's my Jacobi identity. And you can go home and check. As long as these legs are on shell and these gluons satisfy the physical state conditions, then you'll find the numerator obeys the same Jacobi identity. And you say, oh, that's very amusing. But in fact, right here is, if you know what you're looking for, the secret of perturbative gravity is to be found right here. Okay, what's the secret? Let's go look at an endpoint amplitude. So what we're going to do for the endpoint amplitude is exactly the same thing. We're going to write at first everything in terms of cubic diagrams, get rid of the 4-point contact diagrams. If a propagator is missing, you just put it back in, and you write it in this form. And what you do is you impose, you demand, you force that you get the correct amplitude and that every kinematic numerator, let's see, there's the polarization vector and there's momenta, that for every color factor, for every diagram, every set of diagrams, let's say there's 3 diagrams that belong together in a Jacobi triplet, there's Jacobi identity, you then enforce that the kinematic numerators have the same identity, and with a key constraint that this be the correct amplitude. Okay, and you just do that construction. Okay, then the statement is, if you want to go from gravity, or from gauge theory to gravity, you simply take the color factor and you replace it with another numerator factor, just like that. Now, you'd say, wait a second, what happened here? It sure looks like magic. And in a way, it is magic. My definition of magic is we don't completely understand why this is true, because for this Jacobi identity to be true, you'd say there's got to be an underlying Lie algebra behind it, or infinite dimensional Lie algebra. There's some underlying algebraic mathematical structure. We don't fully understand what it is. In some cases, we know exactly what it is, but generally we don't. But never mind whether we actually know where this comes from. We can prove that this is true. So there's all sorts of proofs in the literature, some based on string theory, and there's others based on looking at recursion relations. And the basic idea is, once gauge theory is arranged in the right way, meaning that these Jacobi identities are satisfied, we can immediately get gravity amplitudes. Okay, and by the way, this thing, it cries out for a unified description of gravity with gauge theory, because if you look, you see these numerators, they're like the building block for the amplitude. The same one that appears in gauge theory appears in gravity. So clearly these theories belong together. Presumably something along the lines of string theory. Not that this is a proof of string theory, but there's something very interesting and profound happening right here. Okay, so what this tells us is gravity, in a very precise sense, is a double copy of gauge theory. We know the translation rules. We know how to do this at tree level, and by this unitarity method, we now know how to do it to arbitrary orders of perturbation theory, arbitrary loop orders, by using the unitarity, because any property of tree level can be translated into loop level. And this has been used to study some problems in supergravity. It's a basic question about the divergence properties, the ultraviolet divergence properties, the non-renormalizability properties of supergravity theories, going to very high orders and directly studying those questions using in a sense, the only proper way of doing it is to actually just calculate whether it's finite or divergent. I'm not going to talk about that today. I will talk about instead another application to phenomenology, which is to go after very high orders of perturbation theory in general relativity. Okay, so I think everybody knows about gravitational waves. The era of gravitational waves, of wave astronomy, is here. And by the way, I know exactly the minute I decided I was going to work on that. It was when I saw the paper and someone told me that the power that was emitted by the coalescing black holes was greater than that of all the stars in the visible universe, all the power they emit in electromagnetic radiation. That seemed pretty cool. So that seemed like a problem to work on. Of course, the question was exactly what to do. That took a little while longer to appreciate that. But the very first question you can have, okay, very nice, you're a particle theorist. You work on scattering amplitudes. What can you do for gravitational waves? And the first problem you might have is in quantum scattering, we're thinking about microscopic particles, and they come together and they interact, and then you get these unbounded trajectories, sprays of particles, and then you look at the tools. We look at gauge theory, QCD, electroweak, quantum field theory. What does that have to do with the coalescence of two black holes? There's two black holes. Black holes are large objects, kilometer-sized objects. They're not microscopic. And we're interested, of course, in another problem: bound orbits, classical physics, general relativity. They look completely different. But in fact, if you know your effective field theory, then you would immediately say, oh, yes, it's the same problem. And it's basically the question of separation of scales. When you say something is large or small, it's compared to what? And the what is the distance separation between the black holes. If they're well separated, then the black holes could be thought of as points. And also, if the radiation is large wavelength compared to the size of the object, once again, we can think of it as points. Okay, so you realize, okay, no big deal. It's just separation of scales. And with the way the problem we're interested is set up, these are points, then you say, great, okay, we can use quantum field theory. And this was understood quite a while ago. One of like an earlier paper, and even before this, there are papers. Iwasaki, if you look in his paper, you will find Feynman diagrams describing black holes. And the Feynman diagrams are for scalars, scalar particles, which we will interpret as Schwarzschild black holes. Goldberger and Rothstein, they systematized this all. They understood effective field theory. They applied exactly the systematic procedures of effective field theory to this problem, and we rely on these basic ideas. They're very basic to effective field theory. Anyone who does effective field theory would immediately know that black holes and gravitational radiation is exactly in our wheelhouse. There's no problem. There's no great leap in what you're supposed to do. Of course, here we have to go to the classical limit. So you have to understand how to take the classical limit, and then we also have to understand how to go to the bound orbit case, which it turns out is not too hard, at least in the simpler cases. Okay, so you may ask another question. Okay, scattering amplitudes. Well, we want to compare that, correct Newton's potential. So what do scattering amplitudes have to do with Newton's potential? You can ask that question, because that'll be the first thing you want to do, is correct Newton's potential. And the answer is it has everything to do with Newton's potential. So the scattering amplitude, here's what it looks like. If you, it's written in momentum space, and then if you go to the static limit, that's to get Newtonian, then you'll see it just goes to G Newton 1 over Q squared, just following just Feynman rules, point particles. And then when you look at this, say, oh, let's see, if I Fourier transform this, I get Newton's potential. Or normally it's done the other way around. They start with Newton's potential, and if I want the scattering amplitude, then I take its Fourier transform. So the amplitude is the object we're interested in. Okay, so that's the first really nice thing, that we don't have to twist our knowledge to make it fit into the problem of gravitational waves and the corrections to the Newton's potential. It's something pretty natural. Of course, as you go to higher orders of perturbation theory, even though the basic idea of what I told you, that the amplitude is the potential just for a transform, that's basically still true. It's just a little more complicated because I guess it's higher orders of perturbation theory, and there's all sorts of double counting and other things you have to take care of. Okay, so what's the problem we're after? It's the waveform, which is in a sense the only thing that the gravitational wave detectors can measure. They measure waveforms, amplitudes, and phases, and that's what we're after. The part that we're looking at is when the objects are separated. So we use perturbation theory. Okay, and then there's a merger, and then there's a ring down where you can use different perturbation theory. The merger used numerical relativity, and you have to put this together into one package. And the systematic corrections to Newton's potential, that's from the beginning of time, meaning Einstein, Infeld, and Hoffman did first post-Newtonian, and then over the years, people have been pushing out to second post-Newtonian, third post-Newtonian, fourth. Fifth is mostly done. Maybe there's a few issues left, but it's pretty much there. Now, what got us into the field is this paper, 2017. And it's actually a very amusing paper for its clarity. I've never seen a paper like this. It's a request for some help, but not only is it a request for help, but it's directed to us. It says in the abstract, so you don't even have to read the paper to see what this paper is, why this paper was important. Just look at the abstract. And we urge amplitude experts to use their novel techniques to compute two-loop scattering amplitudes of scalar masses from which one could deduce the third post-Minkowskian effective one-body Hamiltonian. Well, it was certainly very hard to resist an invitation with this kind of clarity. And why was Thibault Damour, why was he asking for help? And the answer can be found on this plot here. These are the future detectors. So here we are today. There's LIGO. And if the way to read the plot is the further down you are, then the more sensitivity. And then you look here, the Cosmic Explorer in some frequency range, you say that's a factor of 100. So we have to do 100 times better in sensitivity on the theory prediction. So if you're interested in discovering some kind of new physics, whatever it may be, you need to be able to interpret that signal. If the answer of a beautiful signal from the future detector is, well, we don't know because our theory is not good enough, right? Did you make a great discovery or a boring discovery and you don't know because your theory is not good enough? That's not acceptable. So we have to push the theory 100 times better. What do you need to get 100 times better? Well, we don't know exactly since we haven't done the calculation, but rule of thumb would be we're going to need about 2 more orders of perturbation theory. And those of you who have done some perturbation theory know what each order of perturbation theory means. It's like climbing Mount Everest. Each order compared to the previous order is a serious challenge. And that's the problem. The challenge requires all hands on deck, so to speak. This is not a simple challenge. Okay, and our plan is, of course, to do our part to help with this. And in fact, it's not just one technique. So I'm going to be talking about this post-Minkowskian. Let's start with numerical relativity. Numerical relativity is very good when the mass ratio is not very large or small. That's the mass ratio between the two black holes. When the separation is small, then that's the powerful technique to use. And when you go to a larger separation and you get small eccentricity, post-Newtonian is a good tool. If you get the high eccentricity, you can do post-Minkowskian. If you get to large or small mass ratios, then you'd like to use a technique called gravitational self-force, which is exact in Newton's constant, but perturbative in the mass ratio. Right, so each one of these different techniques work, and the one that we use that's very natural, it's post-Minkowskian. What that refers to is that our expressions are fully Lorentz invariant. That means all orders in velocity, perturbative in Newton's constant. That's the normal way us particle physicists do perturbation theory. Okay, and then in case we weren't paying attention to Thibault's paper, this was a visit by Alessandro Budana to Amplitudes 2018 that was held at Stanford at SLAC, and she basically told us the same thing there. You should go do this third post-Minkowskian order. She also pointed out if you do that, you get a piece of the fifth post-Newtonian, which had not been computed before. It's a little bit busy, this slide, but this is taken directly from her slide from her talk in Amplitudes 2018. Anyway, it's very clear this was the thing to work on. It fit perfectly with our tools. We should go do it. So the approach is you basically take information ideas from two communities: gravitational scattering amplitudes, all the work and ideas that have been done there. You take effective field theory ideas and you put it together in order to go after post-Minkowskian observables to do perturbation theory. Now, there's many ways of doing this. By now, it seems like everybody who works in the field has their own method. So there's a lot of ways of doing this for extracting the observables from these quantum scattering amplitudes. These days, we use something called amplitudes radial action relation. It's actually an answer to a question of what's an amplitude in the classical limit, and the answer is it should be thought of as the exponential of a classical quantity known as the radial action. It's well known to those people who do classical mechanics, general relativity. There's lots of other methods. There's a very nice method for physical observables, KMOC, which is used, and there's many other methods and ways of doing it, which are some of which are really successful. Okay, so to be clear, what are we after? Basically, we want to take Newton's potential, and we want all the corrections. We want to include radiative effects and all, general relativity effects. All the effects need to be included. Okay, and the place we want to get to is order G to the 6th. That's 6th post-Minkowskian is the place we want to get to, or more if we can get there. So the first thing that the first observation when we started working on this that was pretty exciting is we had all these ideas of unitarity and things have to be on shell, and it turns out that in fact the problem we're interested in meshes perfectly with those ideas. First idea is long-range force. So the two matter, these are black holes. The two black holes have to be separated by propagators. You can't cancel these propagators. Effectively, we can think of these as on-shell gravitons. So these are on-shell. Then it turns out that we're doing classical physics. We need to enforce Einstein's relation between energy and momentum. And because of that, this line effectively is on shell because you have to pick up a residue of a pole on the propagator. So lots of things are on shell and things work very nicely. And our tools fit perfectly well for extracting for the physics pieces that we want. Okay, and that was the first kind of really interesting observation, because it could have been that our tools don't quite work. They sort of work, but it turned out that in fact they align perfectly with the problem. Maybe just a very quick thing of what the idea is. This is actually not how we do it, but it's easier to explain it this way, so I'll do it this way, which is to use the Kawhi-Llewellyn tie relations. So we're interested in this loop amplitude. There's a loop here. And so that'd be a higher order perturbation theory. And we get the loop amplitude by building it from tree amplitudes. So this would be a 4-point amplitude. There's two scalars that represents Schwarzschild black hole, not spinning. And then we have two gravitons right here. So that's a 4-point amplitude. Then there's a 3-point amplitude, 3-point amplitude in gravity. Using Colloquium and tie relations, the double copy, we turn that into gauge theory. And then we start to gauge theory and we compute this. Okay. Now, let me make a long story short since I'm running short of time, which is this was our first calculation on this. This was in 2019. We calculated the 3-point amplitude, and these were the conservative terms that we calculated in the amplitude. Okay. And you can see one thing that's kind of amazing is that this amplitude, that's a two-loop amplitude, okay, there's order G cubed, third post-Minkowskian order. That's what the 3 is here. It's a 4-point amplitude, 2 to 2 scattering. So that's two black holes. Each black hole comes in and then it scatters, comes out. It's a very compact expression. That's the first very surprising thing. After all, this is gravity. It had a number of interesting features. The compactness is one. There's a new feature. There's a log singularity, a mass singularity, which seems a little bit surprising for those people who understand gravity. It's just a feature of the amplitude. It's definitely there in the conservative part. And the other thing that was actually very instrumental for further progress is if you study the mass dependence, there's mass dependence hiding in here. See, there's the mu's and the nu's that carry mass dependence. It has a certain structure that you can then exploit for organizing the perturbation theory as you go to higher orders of perturbation theory. That was observed in this paper, and then there's a comprehensive understanding from Damour. Now you can get also the Hamiltonian. You can extract a two-body Hamiltonian. Roughly speaking, it's just the Fourier transform of that object I showed you. Once you process it properly. And this Hamiltonian, it's relativistic. There you go, relativistic. This would be to the third order in Newton's constant. There it is, third order. Newton is hiding in here in this first coefficient. Sure doesn't look like that way. It looks pretty complicated, but that's because this is fully relativistic. It's Lorentz invariant, so it has all the velocity corrections. If you go to the static limit, in fact, Newton is here. Einstein, Infeld, Hoffman is some combination of these two coefficients, and this is the new coefficient. Okay, the third order that had not been computed before. Okay, and what this shows you is these ideas actually work. Now, you may ask rightfully a good question was, how do you know it's right? Because that you can worry a lot about that. I told you all sorts of strange things. I was talking about double copy, I was talking about unitarity, I was talking about classical limits, quantum field theory. And then at the end, this is supposed to match exactly what a person who does general relativity. Are you sure it's exactly the same thing? Of course, we worried a lot about that. We compared wherever we could. There were these post-Newtonian Hamiltonians, which are velocity expanded, and in the overlap, they agree. There are other checks. Now it's kind of amusing, but it's no surprise. These results were met with initial skepticism. In fact, Thibaut Damour thought our paper was wrong related to the log singularity, the log mass. There was a log m. In fact, he even proposed a different answer. If you look at this paper, version 1, the version 1 tells us all the things we could have done wrong, gives us a different answer. Anyway, we just sat back and waited. The thing we waited for was the calculations that took about another year to do, which is to do higher orders in post-Newtonian. As high as you could go, that was 6 p.m., to pick up terms which Thibaut said must be wrong, and just do the calculation using general relativity methods. And also effective field theory, that was Blumlein's collaboration, and then Bini, Damour, Girolamo, and they worked very eagerly. Thibault was very eager to prove us wrong. Anyway, we just sat back, waited for the answer. It agreed with our answer. So that was very good. There are many other calculations, all sorts of the clarifications of the puzzle, the original puzzle that led to the skepticism. Anyway, the bottom line is the methods are accepted as correct by the community because they have withstood some careful scrutiny. It's the way science should be, right? You should be skeptical of new and strange results, and then you should go check, which is exactly what they did. Okay, now the game is to go to as higher order as you can. So we've done calculations. The next order, also, there's another group did that as well. Other groups, I should say, did that. And then now the challenge is to go to the one more order. And by the way, when I said two orders, I mean two orders beyond this. This is the goal. This is to get the factor of 100 that is necessary to interpret the physics from the future detectors. Okay, so let me show you just a little bit. This is what the fourth order looks like. Okay, I'll be quick about this since I'm out of time. You encounter all sorts of fun things. If you like mathematical physics, there's your elliptic integrals. People like elliptic integrals. This time around, we had no trouble at all convincing the community we did it correctly because Thibault and company were very, very helpful. They were eager for our results, so they got ahead of us on the first three terms in the velocity. These are velocity terms, and so this is done post-Newtonian. They gave us the first three terms in our language. See, that's an amplitude. They gave us pieces of amplitude, the scattering amplitudes that we could compare to. And life was good because once we calculated, once we thought we might have the right answer, then all we did was series expanded velocity. We matched their three terms, and everybody was happy and appreciated that the calculation was done correctly. And how good is this stuff? It's actually quite good. Here's some comparisons. This is one of the comparisons that have been done, where you start, this is through fourth post-Minkowskian. What you do is you compare to numerical, this is numerical relativity. And you work hard to push numerical relativity into weak coupling. And then what you do is you push the post-Minkowskian perturbative results into strong coupling using a resummation, effective one-body resummation. So it's professional level resummation that's done. And what you can see is the numerical points, fourth post-Minkowskian, resummed, that's the blue curve. It's bang on the numerical relativity. Now you might say, oh, good, that means you can stop. No, it's not what this says. It says exactly the opposite. It says it's working, you should continue, right? Because we're looking for that extra factor of 100 improvement in the precision of the predictions. Okay, so now, I just have a little bit more. So we're doing now the next order. Everything is straightforward. Everything is under control. One part is hard. We're still working on that. The integrals are hard. The computer programs that we import from collider physics are no good. You need to rewrite all those programs. We have been rewriting it. There's a competing group. They have been working on rewriting one of the other programs for doing integrals. The other program is called Kira. The program we use is Fire. Oops, wrong way. Okay, what's the problem? Here's one of the, let me just show you a little taste, very quick. This is a typical integral that we have to do. It's got lots of propagators. There's 13 propagators. There can be 9 irreducible numerators up here. And that's a monster integral. If you try doing this using the standard techniques, it becomes pretty explosive and it's very hard to control it. The standard programs will not work. No public code can deal with this. And so you have to rewrite all the codes, and that's being done. When armed with those codes, it'll feed back into QCD. make it possible to do even more complicated processes with with um, in collider physics in QCD. Okay, so just let me be quick about one little thing that's very important. So these algorithms for doing the integrals, they're based on using what are called integration by parts relations, which generate extremely large linear systems. There are millions of unknowns. You're trying to invert a matrix 1,000,000 by 1,000,000. You need to do it analytically. And the question is, how do you do that? And the answer to that question, if you haven't seen it before, is finite field reconstruction. It's awesome. It's absolutely amazing. Even on one CPU, you can run 1,000 times faster to invert a matrix. If you now want to go 1,000,000 times faster, get yourself a supercomputer. Okay, that's me visiting the NERSC Supercomputer Center to convince them to give us more time. That's the Perlmutter supercomputer. And this algorithm is completely trivially parallelizable. You're throwing numerical points. You're doing it in what's called a finite field, so it's prime number arithmetic. It's an extremely magical algorithm. It's unbelievable how fast this thing is. Of course, we still need supercomputers because our problem is extremely difficult. Now, right now, we need supercomputers. The current status of the programs is we need supercomputers to do fifth post-Minkowskian. In order to do the next order, I know exactly what we need. We need to continue working on the algorithms to make it so we don't need a supercomputer at this order, and then we're going to go on to the next order. Let me just quickly show you. Okay, this is a paper we just wrote. It's the wrong theory. It's a paper of n equals 8 supergravity. It's the right problem, but the wrong theory. And it's just to show you that there's progress. And there's also progress from this other group where they've done a piece of the general relativity. And by the way, you get some cool integrals. You can get to use the word Calabi-Yau all you like. So you get some pretty cool mathematical integrals. It's very encouraging, the progress that's been made. The basic outlook is the techniques work. There's lots of different problems you can work on. The one I spoke about here is pushing state-of-the-art to higher orders in Newton's constant, waveforms. There's a lot of papers on that. Finite size effects, tidal effects. Spin is a big deal. A lot of people work on that. Absorption effects, renormalization effects. By the way, if you think renormalization is only in quantum field theory, you are not correct. It's also true in classical theory. Renormalization is encountered. The exact same renormalization we encounter in quantum field theory is encountered in the problem of gravitational wave physics. It just happens at very high orders of perturbation theory. That's the only difference. So it's very cool that all the knowledge that we have on renormalization can be imported to the problem of gravitational wave physics. Okay, and all the standard quantities can be computed, and the formalism is far from exhausted. So to meet this challenge, we need some friends. So this is the GW Sky project. It's one of these ERC synergy grants. So there's me, there's Enrico Barusa, astrophysicist, and the environments beyond general relativity is what he's interested. Okay, you need a guy who knows a lot about nonlinear strong field dynamics. It's a highly nonlinear theory. Strong fields is important. And then you need an expert. That's Alessandro Bonanno, and there's Martin Vandermeet. You need an expert in gravitational wave modeling, the effective one-body approach, the interpretation. That's Alessandro. Okay, so we hope to meet the challenge. It's a serious challenge, but at least we have a great group of people to work on this. Okay, so the summary for my talk is scattering amplitudes. They give us a new way to think about certain problems of current interest in general relativity. We follow Feynman's approach. Massless spin-2 gravitons are all you need to derive general relativity. This double copy, it gives us a unified framework for gravity and gauge theory. If you combine the EFT methods with these amplitude ideas, there's a powerful tool for doing gravitational wave physics. We're pushing to the next order, order G to the fifth. We have an organized project for dealing with the challenge of meeting the precision of the future gravitational wave experiments and the ongoing experiments as they improve their precision. And there's various directions to work on: high orders, resummation in G, spin, finite size effects, radiation, dissipation. And the final summary is the Amplitudes viewpoint that gravity and gauge theory belong together is powerful, and I think we can expect more progress in the coming years. Okay, thank you.
All right, thank you very much, Professor Bern, for the very nice overview. So we have plenty of time for questions. You can either raise your hand and ask the questions, or you can write on the chat, and I can read out your questions.
Oops, it is. Oh, something is wrong. Let me go back.
Okay, so let me get started with the question. So, in one of some of your last slides, you mentioned about this spin effects and finite size effects. I mean, how much complicated the calculations would be once you include these effects, like in terms of introducing.
Well, yeah, that's actually an interesting question. So, in principle, it's very straightforward. Finite size effects are, in practice, also very straightforward. The language is perfect for effective field theory. It's a set of operators, higher dimension operators, that incorporate the finite size effects, the spin effects. In principle, the spin effects are also very straightforward, but the practice is much more complicated. It turns out spin is endlessly subtle and has endless complications. Well, it never ceases to surprise me how much effort it takes to do it correctly and to really understand the nuance of it. All sorts of subtle effects having to do with some of it is the very definition of what you mean by spin. Even like very trivial problems, like how did this person define the spin vector and how did that person define it? That you can spend quite a bit of time straightening that out. And there's all sorts of other issues, also more theoretical issues about what exactly are the degrees of freedom of spin that you should be keeping or not keeping, for example. And I'm sure that it's going to take quite a while until the thing is completely unraveled and agreed upon, and where people can say, "Oh, it's very simple." That's going to take quite a bit longer. But the principle is pretty simple. You just write down all the operators. You know, it's an effective field theory, and you just start writing down operators, and then in that effective field theory, once you write down all the operators, you have all the possible interactions captured by the Wilson coefficients. And then you do some matching calculation to general relativity. Let's say you're doing black holes, and you have to match it to a black hole perturbation theory. Or if you're doing neutron stars, somehow you're supposed to match it to models, which I'm not sure how well you could do that, or match it to data to extract Wilson coefficients straight from data. But so the principles are straightforward. Practice can be quite difficult.
Can I ask a question?
Sure.
Yeah, so could you show the slide 17, please?
Sure. Sure.
So in this KLT relation, you have a factor of I on the right-hand side.
Oh, yeah, that's there for a pretty stupid reason. It's because we use Feynman's convention where the amplitude has an I in it. So basically,
okay.
the imaginary part is actually what normally you'd call the real part of an amplitude. It's just following the rules of Feynman diagrams that causes this I. So in a sense, the I is there just to remove the fact that Feynman put an I into his Feynman rules from the way the overall phase is defined. So there's nothing. It's nothing profound.
Okay, thank you.
It's just to make it look strange. Yeah, it's a really cool relation. It's pretty amazing. You can go off and ponder the question of how Einstein's the Einstein-Hilbert action can possibly incorporate this or encode this. That's to this day, it's a complete mystery how that works. Despite the fact that we have there's a lot of understanding, of course, about how to rewrite the Einstein action in some very nice ways. Clifford Chung, for example, has a very nice paper on that. But how exactly to find these relations out of Einstein gravity done the traditional way through the action is still a complete mystery. And there may be a simple answer, but despite considerable effort, no one has been able to figure out how to do it. It's actually kind of amazing that there can be a simple relation that you can explain this essentially to anyone, anyone who's interested in physics, this relationship, but to understand this relationship following a traditional path is extremely difficult. Well, it hasn't been done yet. So you can marvel at the existence of these relationships.
All right. So do you have more questions from the audience? So I have another question. So in your talk, you discussed this 2-to-2 scatterings. So like higher multiplicity scatterings, would it be useful? I mean, what kind of information one could extract in this?
Oh yeah, right, absolutely. So let's actually. Let me actually go back to this thing. Yeah, so let me go to that list. So of course I didn't talk about that, but let's suppose you're interested in the waveform. So that seems like something. Oops, right here. It says waveforms. Okay, let's go back. Waveforms. So the waveform is described by a 5-point amplitude, and there's a direct connection between the 5-point amplitude and the waveform, because that graviton that comes out, even though you might think it's a quantum graviton that came out, it can be reinterpreted very directly in terms of the classical waveform. So the answer is 5-point amplitudes are waveforms. Compton scattering, for example, graviton comes in, graviton goes out, would be, you could use that to describe, for example, bending of gravitons. It's like bending of gravitons around black holes. Or if the photon comes in, you make it a photon scattering, a Compton scattering, like a true Compton scattering of photons, then that can be interpreted directly in terms of bending of starlight calculation, the famous calculation that Einstein did. So each one of these amplitudes can be reinterpreted in terms of some classical quantity. And the part that's most amazing is that you might think that there's a huge gap between a 5-point amplitude, so it's a graviton emission diagram, and a waveform, that they're completely different because one is quantum and the other idea is classical. But in fact, the gap is tiny. They're the same thing. The first approximation is the same thing. And there's precise formulas of how to calculate, using 5-point amplitudes, how to calculate these waveforms.
Okay, all right.
Yeah, which, by the way, it's all very cool that there's such a simple connection.
Okay, great.
Can I have a question?
Sure.
Yeah. Thank you for your nice colloquium. So, I mean, this double copy idea that the Yang-Mills scale equal gravity is based on string theory, where namely the two open string combines to one closed string. Naively, I would think that the gravity theory should be the gravity of string theory, where you don't have not only the Einstein metric, but also other form fields like dilaton and B field.
Right.
And what do you think about this?
Yes. So indeed, you are actually right that the natural double copy, for example, well, suppose you take two gluons, it's two states. You multiply it by another gluon, that's four states. Gravitons have two states. So what are the other two states? It's exactly what you said. There's a dilaton and an axion or antisymmetric tensor. So you might think that this cannot be used in gravity, in Einstein gravity, that you have a problem. That you, basically that the double copy naturally gives you the wrong theory. Okay? That's what you might think. And more or less you are right about that. Yes, it does naturally want to give you the wrong theory. But right here, I stuck something in, which is, it's basically these gravitons here, right? You don't want to allow a dilaton, and you don't want to allow an antisymmetric tensor. So you right here, you stick, it's a cut leg, so you can put in a physical state projector. You can project it out, get rid of it.
You did it by hand?
Essentially by hand. And in fact, I did it right here. You see, it said that the helicity is plus minus. And if you look carefully, you'll notice there's a correlation in the double copy. It's the same helicity here and here. And that, in fact, is all you need to project out the unwanted states. So at first sight, indeed, and this is part of the magic, you could say, at first sight, it looks like this cannot be done very well. Oh, and by the way, when we started talking about this very early, every time I would meet someone, for example, Alessandro Budano, or whoever it was in general relativity, they would always ask me the same question. And the question was always, it was basically the same as your question. They would always say, can you deal with the dilaton? You know, this double copy, have you dealt with it? Is it under control? And I always tell her it's under control, don't worry. And then, of course, next time I still get the question. And the day they stopped asking the question is the day we produced this answer. And the day, you know, and also the checks that were done, right? So that in the list of questions, you know, that are worrying is if you know about the double copy and you know how it works, you would think that you have the wrong theory, not Einstein gravity. How do you know you took care of all that? And of course, the answer is, you know, our friends confirmed it in the correct theory. We, of course, knew it was correct because we understand the projections to remove the unwanted states, how that works. It's very straightforward. We haven't had any trouble at all from the dilaton. We just get rid of it immediately. And it's because it fits very nicely with the unitarity method. If we didn't have the unitarity in the cuts, where we could access these intermediate gravitons as physical states, then indeed we would have a serious problem, as you alluded. And in fact, the community in the beginning, everybody was worried about this problem. You know, it was, I don't know, 6 months of people asking the same question all the time. Every time I get the same question, exactly the one you had asked. But I'm happy to report that today no one asks this question who's inside, you know, who works on gravitational waves, because they know we can control this problem.
Thank you.
And it's a good question. You know, an important question that we have to deal with.
Thank you.
Yeah. Oh, I see one more question, maybe a raised hand from Ko.
Yeah, P1, I think he asked the question before.
Or maybe he already asked. Yeah.
Yes. So I'm just curious about this G to the fifth calculations. Like you showed this complicated IBP reduction that you
Yeah.
have to tackle, and it's amazing that you have these 22 propagators, 13 propagators and 9 ISPs. I was wondering if this is the main bottleneck in computing
Yes.
this due to the fifth contributions. What about the computation of the master integrals? Like, is it under control?
Yeah, those I mean those are also a pain in the neck, but yeah, those can also those also have their own issues. Cleaning up the differential equations, putting it in a nice form. Yeah, I mean, in this paper that we did, where was that paper? Yeah, this paper. Some of it is done analytically. It's called the first self-force sector. Some of the integrals, there's a certain sector you can do analytically, and the differential equations are no problem, and it's all very straightforward and very clean. There's sorry, wrong. This one, this one. So this would be the fifth order. Some of the master integrals, the differential equations, are no problem at all. But there's a sector. It's where these Calabi-Yaos live. That's a lot of fun cleaning that stuff up. The basic technique that has to be used, because nobody knows what these functions are anyway, or they're anyway defined by the differential equations, you do series expansion. So that can be a pain in the neck, but that's not you could say, the ultimate bottleneck. The IBPs have to be brought under control, and then this is also another part that's very hard to do. I think anywhere you look, there's a lot of trouble. Anything related to the integrals, everything that's not an integral is under control. I don't know if I would say easy, but it's definitely a minor part of the problem. The only problem, the first approximation, probably several more orders of perturbation theory. The only real problem is integrals. That's the bottleneck.
Yeah.
But we're bringing it under control. It'll take a while longer.
Okay. So do we have any other questions from the audience before we close the colloquium? All right. So yeah. So I think I think we can close the colloquium. So let me thank again Professor Zvi Bern for the very, very nice colloquium and for your time.
Thank you.
Let's all thank Professor Zvi Bern again.
Yeah, and next time I'll come in person.
We will. Yeah, we look forward to it. Yeah, thank you very much, Zvi.
Yeah, see you then. Bye.